Today, we will talk about molecular orbital theory, which is perfect because it is called MO theory. It is almost never called Mo theory, but since it's almost Movember, I've got a little paper mustache on today. We'll see how long it lasts. Now let's talk about molecular orbital theory, or MO theory. Molecular orbital theory, MO theory. In this theory, all of the electrons belong to orbitals associated with the molecule and not any one atom. And that's an important distinction. So all of the bonds that we've talked about have been sharing electrons from each atom, and we've been talking about overlap of orbitals, but these are atomic orbitals, meaning orbitals from each atom. And we've hybridized them, but they still belong to each atom. Now let's talk about MO theory. MO theory is much more complicated, but entirely correct. So it is based on quantum mechanics and quantum mechanical versions of the electron and atoms, and so it is correct. However, it is much more complicated, and therefore the biggest molecule that will be on the exam has 2 atoms. So it'll be entirely correct, but it's so complicated that it can't deal with, or it can, but we can't deal, let's say, with molecules bigger than that, because then it gets into very complicated math. And so while Lewis structures and overlapping of atomic orbitals is less correct, it is easier to think of molecules, and it works, I would say, greater than 95% of the time, and that's what we typically use. Now, let's get into it. MO theory of hydrogen, the electron has wave-like properties that are described by the wave function psi for the 1s orbital of hydrogen. And now, if we take 2 of these hydrogen atoms and draw their wave functions, and we've done this before for 1s for sure. 1s, it just looks like, if you go from the nucleus, a downward sloping function away from the nucleus. And while we haven't done it in both the x and negative x directions, we can imagine that on the other side of the nucleus, we get the same kind of function. And those are supposed to be identical. And this is for a hydrogen atom. And it's describing the electron. And for another hydrogen atom far away, same thing. Again, supposed to be the same thing. And these are the wave functions as a function of radius and on each side of the nucleus. Nothing new there. Now what we're going to do is we're going to bring these 2 together and allow these 2 to overlap. And what that's going to look like is something like this. And I'm going to keep to the same color here because we'll switch other colors. And what you can see is that there's an overlapping region. And so where they overlap, there's 2 possibilities. As the 2 atoms come together, the wave functions can interfere in phase, and in phase is going to create a bonding molecular orbital, and in phase means constructive interference. And that means they're going to add. And what that looks like is, again, we'll try and draw the same 2 axes here. And where there's overlap, it will be taller. And outside here, this will be pretty much the same. And so this is a picture of the in-phase overlap, and we're going to add. And what we're going to see, so this is just the wave functions, but when we make a bonding molecular orbital, we will do this too. We will take two orbitals, we will add them, and when we add them, it will get bigger, so there will be more probability of finding the electron. And again, these are just the wave functions to give you an idea. Then down here, for out of phase, it'll be destructive interference, which means subtraction. And for destructive interference, well, we can do, let's draw a picture over here. And we'll draw the same thing. So you can subtract them, and one way to subtract them is to keep this one here, but then to take the negative of the other one. And here I'll do this one in red, and I'll flip my page upside down in an attempt to, there we go. And so now you can see that right in the middle, they exactly cancel out. And so our overall function will come up. It'll start to come down. And then there will be a point where the wave function is 0. Then it will come through here and sort of curve up. And what we will see is that in eventually what we'll call the antibonding molecular orbital, we will see that there is a node halfway in between the nuclei. Additionally, we will see that there are two different phases for the portions of the antibonding molecular orbital. And we've seen this before with p orbitals. P orbitals, remember, had two parts, and one part had what we would call positive phase, and the other part had negative phase. And we didn't say that meant anything other than they're different. So we might call this one positive because it's at the top, and this one negative. So there's different phases that result when we basically subtract, which is destructive interference. And these are the wave functions. Now onto pictures of the bonding molecular orbital for two hydrogen atoms. So, and for hydrogen, of course, we're talking about the 1s orbital. And then we have another one, and we're going to be adding these since this is bonding molecular orbital. We are going to be adding in phase, also called constructive interference. So there we go. So we have two of the same thing. And our process for this is always the same. First off, take off your fake mustache. Second off, then push the two orbitals that you're forming the molecular orbital, so these are atomic orbitals again, push them together until they overlap. Well, I drew them a little far apart, so I'm going to draw them a little bigger here. So something like that, where you have a clear area where they overlap. And just like before, where they overlap, it's going to be bigger. Where they don't overlap, it's just the same. And here we go. So it's going to come up like this or something like that. And what does this, so the green around the edges is the actual molecular orbital, or MO. And now let's talk about this a little bit. So we will decide whether this is a sigma or a pi molecular orbital. So sigma molecular orbitals are going to have the electron density along the two axes. So this is a sigma molecular orbital. And it has a subscript of 1s because it is made out of 1s atomic orbitals. Okay. Right. And so now let's do the same thing, except do antibonding. And antibonding, I'll start with this picture here. So for this picture, where they overlap, they subtract. That means that right in the middle here, let's see, so it looks something like this. And I'll draw this again. But there's a node right here in the middle. And a node still means the same thing it did before. A plane in which there is zero electron density, zero probability of finding the electron. And so we subtracted them. Let me draw this again over here. Something like this. With a node in the middle, because we've subtracted the area where it overlaps. Something like that. This is still, although I drew them a little, so it should be symmetrical here around the x-axis. But this is still a sigma bond because the electron density lies along the x-axis, or the axis of the nuclei in this case. And then it's made out of 1s orbitals, atomic orbitals. And we just put a little asterisk there. That's the signal that it is an antibonding. So, antibonding. Molecular orbital. And so, a couple things to keep in mind here. So first off, all we're doing is adding and subtracting orbitals. Orbitals have wave functions. So it will also turn out that since we're subtracting one of these from the other, there still will be differences in phase here. So, and again, they're just different. And then lastly, and I can't remember if that's covered on the next slide. We'll talk about that next. But 2 atomic orbitals make 2 molecular orbitals. So we're ending up with the same number of orbitals that we started with, just one of them is a bonding, and we'll see that this bonding one is lower in energy on the next page, and one that is antibonding. And we might as well discuss why now. You can see that in the bonding molecular orbital, and this is a general trend, that the greatest probability of finding the electron is between the 2 nuclei, where it can be attracted to both nuclei. That's why it's low in energy. And exactly in the middle between the 2 nuclei is where the electron cannot be in the antibonding molecular orbital. So this is going to be higher in energy. And this one's going to be lower in energy. And it's true that in this description, I've said that this bonding one is lower in energy. I want to further add that it's lower in energy not only than the antibonding one, but it's lower in energy than the 2 atomic orbitals. And this one's higher in energy than the 2 atomic orbitals. And what we can think of is, like previous pictures that we've taken, where we ask the question, why do atoms bond? They bond because they're attracted to each other. That attraction takes them to a lower energy place. The lower energy place that is the bond between two hydrogen atoms, we now have a name for it. It is the molecular orbital, the bonding molecular orbital. Okay, now one more slide here. This is going to be a molecular orbital energy diagram, and it's going to have energy, arrow on the left. It's going to have a hydrogen atom right to the right of that. We're going to leave this space blank for a second, and we're going to have a hydrogen atom on the other side, and we're going to have our H2 molecule in the center. And so for each of the hydrogen atoms, we're going to draw its 1s sublevel. And you can draw this as a line or a box. Different people do it differently. For some reason, I tend to draw lines for these, but boxes are fine. And for a hydrogen atom, there's 1 electron. And in the other hydrogen atom, there's 1 electron. And now, these are atoms. When they do make molecular orbitals, you're going to draw one of them lower and call it sigma 1s. That's our bonding molecular orbital. And equally higher, sigma star 1s. And this is true. There's a splitting of these two. One's lower, one's higher. And at least for this one, because it's relatively simple, we will draw little dashed lines connecting them. And that's to give you the idea that these molecular orbitals are made out of the atomic orbitals. Okay? All right. Then now we're going to place our electrons from our atom into our molecule. When we do that, electrons like to go to the lowest energy place first. So place electrons in lowest energy molecular orbitals. And molecular orbitals can each hold 2 electrons. 1, 2. So we'll put both of these electrons in the bonding sigma 1s molecular orbital. And we'll ask a question, which is it paramagnetic or diamagnetic? Remember, paramagnetic means at least 1 unpaired electron. Diamagnetic means all electrons paired. We see that for hydrogen, H2, all electrons are paired. The molecular orbital electron configuration for H2 would then be sigma 1s 2. And so similar to what we had previously drawn, which was just 1s2, now we get sigma 1s2. And bond order in comparison to Lewis structure, well, for molecular orbital energy diagrams, you take bond order is going to equal bonding electrons minus antibonding electrons divided by 2. And we can see that we have 2 bonding electrons. We have 0 antibonding electrons. Divide that by 2, and we get a bond order of 1. And a bond order of 1 is equivalent to a single bond and that's what we would predict if we drew the Lewis structure. A single bond between the 2 hydrogens. And what we will find is that the vast majority of the time, Lewis structures and the bonding that we talked about before, where we get a single bond in the Lewis structure here, and we get a bond order of 1 using molecular orbital theory, they will agree. However, if there is a difference, it is molecular orbital theory that is correct, because it is 100% correct. And we'll see that coming up one of the main places we can look for it.